Welcome to another podcast. In this episode, we're going to be taking a look at a new class of equations called Euler Equations. In some sense, an Euler equation is just an equation that's slightly removed from the constant order equations that we've been looking at so far. In fact, to get from an Euler equation to a constant coefficient equation, there's just a simple substitution that you need to make. It's also an example of our first singular equation. So an Euler equation is an equation of the form x squared y double prime plus alpha x y prime plus beta y equal to 0. And this is where alpha and beta are constants. And what you notice is that there is a quadratic x squared plus alpha x plus beta as the coefficients of the terms. For this particular problem, since I did claim it's singular, let's go ahead and look at that by dividing through by x squared. Alpha x divided by x squared is alpha over x. And then here with beta, when you divide by x squared, you're going to get beta over x squared y equal to 0. So if we were testing this, if we take the limit as x goes to 0, because I want to expand about the point x equal to 0, and if you look at the limit as x goes to 0 of x times alpha over x, this limit is equal to alpha. Since alpha is a constant, we're not assuming that alpha is infinity. It can't be in this case. So that one checks out for it being a regular singular point. Let's look at the other one. If you look at the limit as x goes to 0 of x squared times beta over x squared, then that is just the constant beta. Because of that, these two conditions together say that if I want to expand my solution about the point x not equal to 0, then that would be a regular singular point. So this is the first singular point equation that we've looked at. In fact, it's the simplest singular point equation there is. The solution format basically goes like this. You're going to guess the solution is of the form y of x equal x to the s for s some constant value s. Now, this is very similar to what we did when we first talked about the characteristic equation and solving constant coefficient equations. We assumed that it was an exponential in that case, because when you take the derivative of an exponential, you get back an exponential. Here, when you take the derivative of x to the s, you get back a polynomial. And because we have polynomials for constants here, this makes a good guess at a possible solution. Now, the easiest way to go about talking about this is if I plug this solution in. So I'm going to plug in y equal x of s to the equation, and I'm gonna keep things in terms of this equation that we started with, not the simplified one. So if I plug y equal x of s in to x squared y double prime plus alpha x y prime plus beta y equal to 0, then the result of that is we've got x squared times, now notice, y double prime, I'm going to get an s and an s minus 1. X to the s minus 2 come down. So that is y double prime. Next, I'm going to get an alpha x times y prime. And y prime is, let's see here, it is s x s minus 1 plus, and then I'm going to have beta times y, which is xs. So I've got my y double prime, and y plugged in. I'm going to set this equal to 0. What you notice here is the powers work out perfectly. You've got an x here times an x to the s minus 1. That's going to be x to the s. You've got an x squared times x to the s minus 2. That's also going to be an x to the s. So if you factor out that x to the s, then that gives you x to the s times s minus 1 plus alpha s plus beta must equal 0. So there are a couple of options here. The first option is, well, x to the s could be equal to 0. But if x to the s is equal to 0, that's y equal to 0, and that's trivial. That is the trivial solution in this case. You can notice that if I set y equal to 0, yes, that is a solution. But I'm looking for non-trivial solutions here. And so a non-trivial solution in this case would be if somehow the value of s was chosen so that this equation could be equal to 0. Now, this is a quadratic equation, and so I want to write it in sort of our standard form for quadratic equations, just to get a better look at it. And so for this particular equation, it looks like this. So this equation has a name. Notice that it is not exactly the same as the characteristic equation. In fact, what does the characteristic equation even mean when you have x squareds and x's running around? But, you know, typically, if the x squareds and x's weren't there, we would think of the characteristic equation as being s squared plus alpha s plus beta. So the only difference is this middle term you need to take and subtract 1 from the constant. This is called the indicial equation. So the idea is if you want a solution to an Euler equation, then you need to find a root of the indicial equation. So this is very similar to the method we used for constant coefficient equations where you're finding a root of the characteristic equation. If it's an Euler equation, it's a root of the indicial equation. Because this is a quadratic, there are 3 cases. And you can imagine what those cases are. So let me talk a little bit briefly about each case. The first case is you get 2 roots, s1 and s2, that are real and distinct. So we get 2 real distinct roots. I think it's maybe somewhat obvious what the answer is in that case. You get y of x equals c1 x to the s1 plus c2 x to the s2. But there actually is a problem with this answer. The problem with this answer is it's not defined. So this is not defined if a couple of things occur. If x is less than 0, unless the value s1, s2 are integers, or s is equal to, in this case it would be beta over alpha, where alpha is odd. Yeah, where alpha is odd. Now, that's a lot of ifs, ands, or buts for this. Let me explain what this really means. You would have this pair, x to the s1, x to the s2, where s1 and s2 are powers. We know that you can't stick negatives inside square roots. So where do square roots come from? Well, square roots come from fractional powers. So if s1 is 1/2, then x to the 1/2 is the square root of x, and I cannot plug negative answers into it. So there are, for certain values of x, these things are going to be undefined depending on what s1 and s2 are. Well, the way that we get around that is we actually define the solution to be the absolute value of x, so that it's well defined for all possible inputs. So case 1, Euler equation, there is your general solution. Case 2 is if you have s1 and that's a real repeated root. Now, just like this gave me 2, this gave me a fundamental set, absolute value of x at s1, absolute value of x at s2. We're familiar with this from the characteristic equation. We know that one of the solutions will be the absolute value of x raised to the s1. The question is, what does the second solution end up being? And I can find the second solution by doing reduction of order. And it turns out, I won't spoil it by showing it to you, but it turns out that when you do that, you end up with an interesting value here of absolute value of x to the s1 times natural log of x. So that when you put this together, the general solution in this case is C1, absolute value of x to the s1, plus C2, absolute value of x to the s1 times natural log of x, and typically you'll see it written like this. C1 plus C2 ln of x times absolute value of x to the s1. So this bears a striking similarity to the repeated real case when we had exponentials, in that it was C1 plus C2x e to the x in that case. And so it's very similar to the characteristic equation problem. It's just slightly different. The slight difference here is instead of multiplying by x, we multiplied by t or x or whatever the independent variable was. We're going to multiply it by the natural log of x to get that second fundamental solution. All right, so finally, and I'm going to need to create a little bit of room here. So finally, if we look at case 3 being the whatever you want to call it, the complex root case, then the idea is for that case we have, let me make my eraser a little bit bigger here. For that case, we have a couple of issues, but it's worked out very similarly to the constant coefficient equation case where we're doing the characteristic equations method. Let me explain. If we're in case 3, then we have S1 and S2 that are complex conjugate roots. So for example, S1 is alpha plus I beta, and let's say S2 is alpha. Well, let's not use alpha. Let's use different values. Let's use A and B since we have alpha in our original equation here. So S1 would be A plus IB, and S2 would be A minus IB. Now, what you might think is that my solution y of x would be equal to x to the s, which is equal to x to the a plus ib, which is equal to x to the a times x to the ib. And then I can use Euler's formula here to say, okay, well, x to the a times x to the ib is x to the a times, we would have cosine, in this case, of, well, back up just 1 second. One more step here. This is the same thing as x to the a times, and this is where it gets a little bit tricky. We would do e to the I b natural log x. So I want you to understand that we're trying to use Euler's formula here. So I need a complex exponential to express this. So I make the substitution, I exchange x for e to the natural log of x, which is the same thing as x. And so I can use Euler's formula now to write this as cosine of b times natural log of x plus sine of b times the natural log of x. Now, if you recall, or plus I sine of b natural log of x. And if you recall, when we were looking at Euler's formula and we were looking at the complex case for the characteristic equation, we simply took the real part and imaginary part, and those became our y1 and y2. And so it's no different here. Our y1 is the real part of this expression. So that is absolute value of x to the a, for the same reason I took the absolute value of x over here. Cosine of b times natural log of x, that's the y1 value. And the y2, which forms the second part of our fundamental set, is x to the a sine of b times natural log of x. So this forms my fundamental set in the case where I have complex roots of the end-to-seal equation. And once again, I should prove to you that the Wronskians of all these make them independent. You'll just have to take my word for it. These do form a fundamental set of solutions. You're welcome to try to prove it yourself, or at least show that these are indeed a fundamental set of solutions. You'll read about it a little bit in the textbook as well. But these are now the three cases that we have in terms of solutions for Euler's equations, just like we had three cases for constant coefficient equations. So this is just sort of it's a little bit of a memorization thing, but it should be fairly straightforward from what we did with the characteristic equation. All right, thank you for watching.